Today we're going to do two things. First, we'll quickly learn what it means to consider the implications of a decision. Second, we'll switch to a calculus example about arc length, and I will show you exactly what information I need in order to compute a curve length for your question. When you consider the implications of a decision, you are looking ahead at possible outcomes and how they will affect you or others. Two actions directly support that forward-looking step. Number one, weigh the advantages and disadvantages. Number two, learn more about the situation. Two related actions are helpful but belong in other stages. Pinpointing the problem is part of defining the issue. Deciding if your evidence is biased is part of evaluating evidence before you forecast outcomes. Great. Now, let's pivot to your calculus question about the length of a curve. To compute the length of a specific curve, I need two ingredients, the exact equation of the curve and the exact endpoints, here named capital O and lowercase a. If you share those, I will compute the precise length. Meanwhile, let me show you the general formulas and two clear examples. Here are the three most common arc length formulas. For a function y equals f of x on x from a to b, L equals the integral from a to b of the square root of 1 plus f prime of x squared, dx. For parametric x of t, y of t on t from alpha to beta, L equals the integral of the square root of x prime squared plus y prime squared, dt. For polar coordinates, are of theta on theta from theta 1 to theta 2, L equals the integral of the square root of r squared plus d, r by d theta squared, d theta. Example A. Arc on the unit circle from angle 0 to 60 degrees. On the unit circle, the radius is 1, and the arc length equals the central angle in radians. 60 degrees is pi over 3 radians, so the arc length is pi over 3. Example B. The curve y equals x squared from x equals 0 to x equals 1. We plot the curve on axes and write the arc length integral. The derivative is f prime of x equals 2x. So L equals integral from 0 to 1 of the square root of 1 plus 4x squared, dx. A correct antiderivative is 1/2 x times square root of 1 plus 4x squared plus 1/4 times inverse hyperbolic sine of 2x. Evaluated from 0 to 1, the exact length is 1/2 times square root of 5 plus 1/4 times inverse hyperbolic sine of 2, which is approximately 1.479. To finish your specific question, please share the curve's exact formula and the coordinates or parameter values of points capital O and lowercase a. Once I have those, I will set up the correct integral and compute the exact length.